Hi class, Dr. Searcy here with the video lecture for the textbook for chapter 9. And as you can see, the title of the chapter is Introduction to the T-Statistic. Before I get into what a T-statistic is, I want to do a quick bit of review just to kind of make sure we're in the right place as we begin this lecture today. First thing that I want to remind you of is what standard deviation is. Right, so this is basically something that you've been working with for much of the semester. Right now, you just want to remember the symbols and the formulas associated with it. So we say that there are two forms of the standard deviation. One form is the population form. The way that you obtain it is by calculating the square root of the sum of squares over the number of participants in the population. The other way that you can calculate this is to calculate the sample form of the equation. That's denoted by the lowercase s, and it's still a square root that you're going to find. This time it's the square root of the sum of squares over degrees of freedom. And just remember that degrees of freedom represents n minus 1, or the sample size minus 1. Okay, so keeping that in mind, another term that you want to remember is this type of standard deviation that we've been learning about recently, called the standard error of the mean. Now remember, what we're doing here is we're saying that now when we go to pull something out of a population, we're pulling out entire groups of participants at a time. And as we create a new distribution with those groups of participants, each piece of information that's going in the new distribution is each group's sample mean. Right, so with that, we said that now we've got this distribution of sample means. We've got to create a standard deviation for that new type of distribution. And that standard deviation that we're calculating is the standard error of the sample mean. The way that you obtain it is to take your standard deviation and divide it by the square root of the number of people in your sample. Okay, so why have we been doing that? We've been doing it because the standard error of the sample mean has been an important term that we use in our new z equation that we've been using. The z for the sample mean distributions, right? So like for instance, in chapter 8, when you calculated the z-score, the way that you calculated it was you took the sample mean and you subtracted the population mean from it, and then you divided that by this standard error of the mean. Why were you calculating a z-score? Well, remember, the purpose was you were looking to see if this effect that you found, right, maybe this difference between a sample mean and a population, if that effect was significant or if it was due to the independent variable. Okay, so how had you been doing that? Remember, in chapter 8, you learned about this 4-step process called hypothesis testing. And the 4 steps were that first, you state your hypothesis. Here I'm writing it as your hypotheses, right? So that's the plural form of hypothesis. And I'm saying it's the plural form because you're stating a hypothesis where there's no effect, and then you're also stating a hypothesis where there is an effect, right? HO and H1. Why are you doing that? Because you're stating what the two potential outcomes of your study are. Either that the treatment did not have effect, the HO, or that the treatment did have effect, the H1. After you've done that, then remember you are locating your critical region. And the critical region is basically that area of the curve that you're going to say is some kind of tail region, and that you're saying that you're looking for whether your z-score is in that region or in that region of the curve. And so when you're locating the critical region, you're basically identifying what that boundary is. But once you've done that, then you are going to conduct your calculations, and basically the calculation that we've been doing is this z calculation. Maybe there were a couple of other equations that came before it, but the point of those other equations was to get a z. So then once you've got your z number, you're comparing it to the z from the critical location, or the critical region, and you're using that information to make a decision. Was the treatment effective or was it not effective? Okay, so with all of this, right, we're reviewing these steps that we had to complete in order to figure out if a treatment was effective or not. One thing that we've been saying that we're using is a z-score to help us figure that out. And so I just want to point out some important things to remember about the z-scores, like some fundamental principles. One is that the z-score that we've been talking about, the z-score for the sample mean distributions, we're saying that in it, the sample mean is going to approximate the mu. Right, remember we were saying that as you pool groups of participants out of a population and you build a sampling distribution with that, the curve of the sample, we'll call this the sample mean distribution. The curve for this should match the curve for the population that you pooled all of those samples out of. Right, so that's this point, first point that we're making here. The two curves should look similar. They should approximate each other. Second point that we're making is that we use the standard error of the mean as this expected difference between the population distribution and the sample mean distribution. What do we mean with this? We mean that the two aren't going to be exactly similar. There's going to be just some inevitable difference between the two curves. And so we're saying that we want to be able to predict or see what the expected difference is between those. Right, so here it approximates it, so it's not exactly the same. We're using this to figure out, well, okay, if it's not exactly the same, can we expect a specific difference? So then the third thing that we're saying is just remember how the z-score formula is working. We're saying that in the numerator is the sample mean. So that could be like the treatment that you've been working with. The mu is the population mean. And maybe one way that we can start to talk about these two numbers being represented is the mu could be like your sample mean before treatment, and your x bar is now your sample mean after treatment. So the idea with this is like, say, maybe for example, we took a group of people who are depressed and we measured their level of depression before meds. Then we gave them the medication and we measured their level of depression after the meds. Right? The whole point of doing this is to figure out, is there a difference? Do the people feel differently from before they took the meds to after they took the meds? Okay, so with that, we're also saying that the z-score always wants to have a standard measure of standard deviation, right? A standard distance away from the mean in the denominator. And because we're talking about sample mean distributions here, we're going to use the standard error of x bar as our standard deviation. Okay, so one thing that we just really want to we really want to understand is this point that I was just making about the before and the after means. Our goal in all of this is to determine if that difference between the after score and the before score is significantly greater than would be expected by chance. Basically what they mean here is if there is a difference between before meds and after meds, right? If there's a difference in level of depression, is that difference due to the medication? Or is it just some difference that would have naturally existed? That's what's being asked here. If the explanation is that the difference just naturally exists, That's what they mean by just expected by chance. So we're looking to see, is this difference greater than would be expected by chance? Is it more than just chance? Might we be able to say that no, it was the medication that caused the difference? Okay, so with that, we're saying that we've been using the z-score to help us figure that out. But often in the field, often when a researcher is actually conducting a study, they find that they have problems with z-scores. What is that problem with z-scores? Basically this. To actually conduct the study, to get the information that's required, typically requires more data than is available. Specifically, what is it that's hard to get a hold of? It's hard to get a hold of that population standard deviation, right? Since we're talking about a population and having to get a hold of everyone in the population, if we're going to be able to say anything about the population, it's hard to get a measure of that score. Okay, so because that's the case, what do? Well, we say that we use the t statistic instead, right? So that is what this whole chapter is about. We're saying that we used to be able to rely on the z-score to help us understand this question about the differences between before and after. But in reality, we often don't have access to a crucial measure, this population standard deviation. So instead, we're going to rely on calculating t statistics instead of z statistics. Okay, so one thing that you just want to remember as we proceed onto this is that t is basically z, right? So we're basically still doing the same thing. We're just going to use a new equation called t instead of z. Why are we going to do this? We're going to do it because we often don't know what the population standard deviation is. Okay, so to help us understand how this process works, I'm going to go ahead and run us through an example problem. That example problem is actually featured inside the textbook. It's kind of an interesting study that is talked about in this chapter of the textbook, in case you want to look it up. But what's happening in this study is, I guess I'll explain it by referring to it as the hot or not moms study. Before we go over like the participant information and the statistic information, let me just kind of explain what was this study all about. What happened in the hot or not moms study? Well, basically the study tested a hypothesis. And that hypothesis had to do with infant looking time at a mom. I'll just kind of say that the hypothesis goes something like this. If you have an attractive mom versus a not attractive mom, and you have an infant, right, some baby, look at the two moms at the same time, the baby, according to the hypothesis, is going to spend more time looking at the attractive mom and less time looking at the not attractive mom. Right, so that's the hypothesis that was being tested in this study. What I want to go over with you is what were the steps of the hypothesis testing using the t statistic. So we're going to run through steps 1 through 4, right, just like you learned in chapter 8, steps 1 through 4 of the hypothesis testing. But as we do, let's just kind of make sure that we understand the pertinent information that we have at hand. We have been told how many participants there are in the study. Now remember what's happening here is they're looking at how long an infant is going to spend looking at the two different kinds of moms. So they got a hold of 9 infants and they took them in a room and they showed them the two different moms at the same time for a total of 20 seconds, right? So they're in the room, kids looking at this mom or at this mom. They're both available at the same time. And both moms are up for 20 seconds. During that time, the researchers are watching the child, watching the infant, and they're measuring how much time is the infant spending looking at either this mom or that mom. Okay, so when they are done, they ended up getting a mean score of 13. What does that mean? They got a mean score that said that the infants, this X13 is for looking at the hot mom, right? So on average, the kids spent 13 of the 20 seconds looking at hot mom, and that must mean spent on average about 7 seconds looking at not hot mom. They did some descriptive statistics around this, and they got a sum of squares value of 72. Okay, so that's the information that we're given about the study. Let's look at how the equation got solved. First, we had step one, where we stated the hypothesis, and we selected an alpha level. Here we're calling it 0.05 for two tails. Okay, so let's look at our first hypothesis, right? The hypothesis that says that there's no effect, there's not going to be any difference between how long the kid looked at hot mom versus not hot mom. Remember that we call this hypothesis H sub O, or the null hypothesis. Okay, what does it say? It's saying that there's no effect. In this particular case, the no effect is that the infants are not showing a preference. They don't have a preference for the hot mom or the not hot mom. What does that look like in terms of a mu statement? It means that for the hot mom, the infants spent an average, population average, of 10 seconds looking at her. That means that then, right, they spent the time, they spent half of the time looking at hot mom, and because it's we're saying 20 seconds, they spent the other half of the time looking at not hot mom, right? So the infants spent their time evenly looking at this mom versus that mom. That is the null hypothesis. It's saying that there was no effect of attractiveness. The other hypothesis, on the other hand, H sub 1, or the alternative hypothesis, says that there is an effect. And what is that effect? That the infants did show a preference. And that would have been seen if the results were where the amount of time spent looking at hot mom was something other than the 10 seconds. Right here we're just saying that it's not equal to the 10 seconds. One thing that's kind of interesting with this is this suggests a two-tailed test to me. Right, and so what do I mean by that two-tailed test? Remember what we're talking about is having that curve and us saying that we've got that critical region where we're going to be looking for the z-scores. And we're saying that the critical region could be either this tail or this tail. Right, so we're going to look for z-scores somewhere under the curve, and we're saying that if we find a z-score in the middle region, then that z-score is telling us that there is no effect, or that HO is true. However, if we find a z-score either here or here, then we say that we reject HO. We say we're going to reject the null hypothesis, and instead we'll accept the alternative hypothesis. Okay, so let's go ahead and look at our critical value that we just kind of set up with saying we've got a 0.05 at two tails, right? So that's in that 0.05 is saying that 95% of the curve is this null region. Okay, so step 2, locate the critical region. We're going to use 2 bits of information to help us do that. This thing that I'm calling alpha, and this other thing that I'm calling degrees of freedom. I believe that I've already exposed you to both of these things, right? Alpha, I said, was that percent that you're going to use to identify where your boundaries are on your curve. And we're saying, oh, we're counting it as 0.05, right? So the 0.05, that's how I'm saying that 95% of the curve is null then. Okay, so we set our alpha at 0.05 for degrees of freedom. You've already learned about this. Remember, it's just n minus 1. So in this case, it is 9 because we have 9 participants minus 1. So our degrees of freedom are 8. Okay, why are we going to use these 2 bits of information? Well, in going and looking for a critical region, we are no longer going to be thinking of our critical region in terms of z values. Now, it's going to be in terms of a t distribution table. This is a table, right, just like that UNT table. This is another table inside your book, and it's on page 651. Basically what you're going to do is you're going to go to this table now, and you're going to look up these 2 bits of information. You're going to look up your alpha level and your degrees of freedom. Okay? And you're going to use those 2 values to help you find your critical region. Okay, so I'll show you how you're going to do this. You're going to go to page 651 in the book. First thing that we're saying is we're looking for the alpha level at that 2 tails. How do you do that? Well, if you look at the t distribution, you're saying that you've got it here on page 651. You've got all of these different critical values. You're going to pick one, but the way you're going to pick one is you're going to look for your alpha value that you're using in the rows here. Notice that there are 2 rows for 2 different kinds of tests. The row on top is for if you're running a 1-tail test. The row on bottom is for if you're running a 2-tail test. Right, so first thing that we're doing, we're saying, oh, I'm running a 2-tail test, so I'm going to look for my percent level in this row. What is the value? It's 0.05. So for the 2-tail row, I'm going to find the 0.05 column of critical values. From here, now that I've got my column identified, the question is, well, which critical value am I going to use? Well, the answer to that is you're going to use it based on your other piece of information, your degrees of freedom, right? So that's this column that you've got going down here. You're going to look up the degrees of freedom that you're using. We said we're using 8. And so when you find that 8, you're going to go across the columns to your column, the 2-tail 0.05, and you're going to use the critical value at that intersection, 2.306. Okay, so we're saying, when I said that I was using a 2-tail test with alpha of 0.05, and my degrees of freedom were 8, and I looked up the intersection of those values on the t distribution table at page 651, I found that the critical region I'm going to use, the critical value I'm going to use, is 2.306. Okay, now remember, the whole idea with this is you're going to do a calculation. The final result of that calculation is going to be compared to that number. Okay, so let's go ahead and set that up. We're now moving on to step 3, where we're going to calculate the test statistic. So with this, I just want to show you the different calculations that we're going to have to run through here. The very last calculation that you're going to do is this t equation, right? Just like we said back on page 1, we're no longer using Z, we're now using T. This is the equation for it. You want to see how this is very similar to the Z equation, right? The numerator is exactly the same. In the Z, you had the sample mean minus this population mean. The denominator is almost the same, but it's just a little bit different, right? It's still showing a measure of standard deviation, but now it's like this standard deviation that's like a standard error, but not a population standard error anymore. Now it's like this sample standard error, right? And the reason why you're doing this is because, remember, you didn't know anything about population standard deviation. So instead, we're going to try and use sample standard deviation information. But not just sample standard deviation, we're going to use sample error from the sample means. Okay, so how are we going to get that value? Well, that's this value in this equation, right? So remember, this thing is called the estimated standard error. The formula for it is it's the square root of sample variance divided by n. What? Sample variance? That term seems familiar, but I don't remember what it was. Well, if you don't remember what it was, it's up here, right? Okay, so first, because it's a lowercase s, remember that we're talking about a sample. Because it's a sample squared, we're talking about sample variance. When, you learned this formula back in chapter 4, and you learned it right before calculating sample standard deviation. So just remember, the formula for sample variance is sum of squares divided by your degrees of freedom, your n minus 1. Okay, so now just think, the whole logic of this is my goal is to calculate this equation for t so I can compare this t to that critical value and help me with my step 4, my decision. But in order to get that t, I've got to get these other values first. So let's kind of just go through what we have to get first. Right now, I really want to get this estimated standard error, but I can't because I don't know what my sample variance is, so I'm going to have to go calculate sample variance first. Okay, well, I can do that because I was given the information to do it with. I was told what my sum of squares is in this experiment. It's 72. I also was told what my degrees of freedom were. Where I got that was I was told my n was 9, so n minus 1 gives me 8. So then that means that my sample variance is 9. Take that 9, I'm going to use it now as the numerator in my estimated standard error, and therefore my equation will become not the square root of 9 divided by 9 equals the square root of 1, which then equals to 1. Now I can use that 1 as my estimated standard error and my denominator of my t equation, and I can solve my t. It ends up being 13 minus 10. Where did I get that 13? That 13 was our sample mean. Where did I get that 10? That 10 was your mu in the experiment, right? We called mu right here. Okay, so this reduces to 3 over 1, which reduces to 3. Now, with this 3, I have my value that I can compare to my t. Now, remember what happens here is I have to say if t is greater than CR, then conclude that treatment is significant, right? If the t that I calculate is greater than the critical region that I've identified, then I'm going to conclude, right, that's my step 4, my decision, that my treatment is significant. Okay, so I'm now going to do that. I'm looking to see, is this T that I just calculated greater than that critical value that I identified? Yes, it is greater, right? 3 is more than 2.306. So for my step 4, I'm going to conclude that I need to reject HO. I need to reject the null hypothesis because baby showed a preference, because the treatment was significant. Okay, so with that, we've just gone through the four-step hypothesis testing process when you are calculating significance using the T statistic. From here, I want to just add a couple of additional comments, and that is that often a researcher won't want to just find out if they got significant results in their study. A researcher will also want to find out information with regard to effect size, right? And so we kind of talked about effect size in previous chapters. I just want to remind you, when we talk about what effect size is, we're talking about this difference between the sample mean and the population. Specifically, we're talking about that difference, in this case, about the before sample mean and the after sample mean. Right, so we're going back to the idea of this was what the group looked like before the treatment, before they got the medication. This is what the group looked like after they got the medication. If there's a difference between the two, we want to measure the size of that difference. We want to get a sense of, well, how much of a difference was there and how meaningful is that difference? So one way that we can calculate that is to use a measure referred to as Cohen's d. I believe that we started to talk about this in chapter 8 when we were still using the z-score. But now I'm just going to note that you can also use Cohen's d when you're calculating t's. When you do, it's pretty much the same equation. It's still your sample size minus your population divided by your sample standard deviation. In this case, it's 13 minus 10 over 3, which gives us an end result of 1. Right, so that's one way to measure effect size. Another way to measure effect size is to calculate what's referred to as R squared. The way that you do this is you take the t value that you've ended up calculating in your step 3 and you square it, make that your numerator in your equation, but then you also make it a denominator in your equation. But in the denominator, you're adding it to your degrees of freedom. So in our present example, we calculated a t of 3, right? The 3 was greater than the 2.306. So when we square that t of 3, we end up with 9. We also said that we had 9 participants in the study, so the degrees of freedom on that is 8. That reduces to 9 over 17, which further reduces to a 0.53. Now, a way that you want to understand this is you can think of that 0.53 as like a percent. And if you're thinking of it as a percent, then the way that you're thinking about it is it's the percent of error explained, right? So it's the percent of this difference explained. I'm gonna add this. I'm gonna say by the IV. What we mean by this is this is the percent of the difference that we can say is due to what you did to your participants. Right, so here we're saying that, oh man, 53% of that error is due to the intervention, right? Or can be explained by saying, yeah, the intervention caused that to happen, the medication that we gave the participants. Okay, so now I want to move on to one other way that we can talk about effect size, and that is with regard to this thing called confidence interval. What is a confidence interval? Well, here I'm defining it as a range of values centered around a sample statistic. And it's used to estimate a population mean after treatment, right? So where would a population mean be after the treatment, after it was found that the treatment was successful, that it did cause an effect? So what we're talking about is finding some range where we could say that mu, right, the population mean after treatment, should be within some interval. Okay, so how do we figure that out? Well, first we say we want to know how big that interval is going to be. The way that we do that is we identify some percent. Right here I'm saying it's a 95% interval. So where we're saying, just like we've been talking about in previous chapters, that middle 95% of the curve. Okay. Now when you do this, there's a formula that gets used, and that formula is mu equals sample mean plus or minus t times that estimated sample error. Okay, so in this example, we're saying that what you're doing is you're solving for mu. And you're going to use these other values to help you solve for mu. But notice that you've got this double operation symbol here, right? A plus sign and a minus sign. What that means is you're going to do this equation twice. You're going to do it once where you're using the addition sign here, and you're going to do it a whole other time where you're using the subtraction sign. But as far as identifying the different values that you've got here, the value that you have here is the value that you got from that information they got about the study, right? They said that the sample mean was 13. And you're even using the standard error that you had calculated before, right? So that standard error of that 1. But as far as this t is concerned, that's another critical value that you have to go look up. The way that you look it up is you say that I've got my bits of information again. I'm saying that I'm looking for a 95% confidence interval. That means on the table that you're going to use, you're going to look up that 0.05 region. Why 0.05? Because we're taking up 95% of the curve. What's left over? 5% of the curve, half here and half there, right? So that's where we're going for the 0.05 region. In addition to that, we're also saying that we're going to look for it on the 2 tails row. Why on the 2 tails row? Well, because since we're talking about having these 2 intervals, we're creating 2 tails. So, and the other thing that you're saying, right, you also had to have your degrees of freedom information. You're going to use the same degrees of freedom information that you'd calculated before. It was that 8 because your sample size is 9. Okay, so I'm going to go to my T table, and I'm going to look those 2 bits of information up. When I do, I'm going back to my T, saying that, and I'm saying that I'm going to use that critical value of 2.306 because it's there, there, and there. So this is then what the equation is going to look like. I'm going to calculate it once here where I'm doing the subtraction operation. And I'm going to calculate over here too where I'm doing that addition operation. So just to start with, we're saying that the mu that I end up getting from this form of the equation is going to equal, so we'll say mu equals 10.694. How did I get that? Well, it was 13, right, the sample mean, minus the t that we found times that standard error. So that's how we got the 10.694. On this side, I'm going to solve for mu, but this time it's going to be 15.306. How am I getting the 15.306? Well, this time it's 13 plus the 2.306 times the 1. Okay, so now what you want to see is I've created my two intervals where mu should fall. Right, and the way it's going to work is I've got one interval boundary here, and I've got the other interval boundary here. What are those two boundaries? Well, 10.694 here and 15.306 here. In the middle, somewhere, should be that mean of 13. Okay, that's everything I've got for chapter 9. Thank you very much, and I'll see you in the odds problems.